Hello students, you're welcome. We are here in the class academy. Our tutorial is on general physics 2, right? Okay, okay, so we in this topic going to consider capacitors, okay, capacitors, and then we'll also look at the capacitance of the capacitor, the capacitance of the capacitor. Okay, we also look at how to calculate the capacitance, how to calculate the capacitance of the capacitor. Okay, so pay attention and remember to write as you listen to the explanation. If there is any aspect you didn't get at the first time, then listen to it again. Okay, and take note of the points that are made. Alright, so you're welcome. Let's continue. Now, let's first look at what is a capacitor. What is a capacitor? Okay. Let's look at what is a capacitor. Now, a capacitor is a device that stores electric potential, okay, electric potential energy and electric charge. Now, a device that stores electric potential energy and electric charge is a capacitor. Okay, now, possibly you must have seen something that looks like this. Okay, and then you have trying to draw a camera that a photographer used. Okay, and then it has something like this. Okay, yeah, so I'm just trying to put something for you. This is like a camera that photographer used, and that camera, it has flashlight. Okay, it has a flashlight somewhere here. Now, if it has a capacitor in it also in that camera, the capacitor in it has to store certain amount of electric potential energy that powers the flashlight. Now, if the battery is low, okay, let me put it this way. According to college physics, this explanation I gave earlier is from college physics. Okay, from college physics. Okay. Now, according to college physics, a camera flash requires a brief boost of power. Okay, it requires a brief burst of power rather. Okay, much greater than the camera battery. Now, this flashlight requires more power than the one the camera requires. Okay, so take note of that. So the flashlight requires more power, more burst of power than what the camera requires. Okay, so the camera battery will not be able to power the flashlight enough. Okay, so the flash is powered by a capacitor. So this is powered by a capacitor. Okay, while the camera is powered by battery. Okay, so and then The capacitor stores up energy from the battery. So the capacitor stores energy from the battery. Stores energy from the battery. Okay, so this is powered by battery. This is powered by capacitor. Now, so what happens on that? According to fundamental, so this explanation is based from college physics. Okay. Now, according to fundamentals of physics, says that the battery can store energy. The battery can store energy at only a modest rate. Okay. Now, too slow. The exact modest rate is too slow for the photo flash unit to emit a flash of light. So the kind of ability that the battery has is not enough to power the flashlight. Okay, so it's not enough to power the flashlight. So therefore, there is a need for another device, which is a capacitor, to be used to power the flashlight. Now, let me use something that you may be familiar with. Some of you use smartphones, and now imagine that the battery of the smartphone is getting low. It's possible that you may still be able to use your camera, but you may not be able to use your flashlight. Okay, so what happens there? When the battery is low and you try to use a flashlight, you may get an indication that the battery is not is low. Okay, so if you now apply it to something like this, so this is powered by battery, this is powered by the capacitor. So the capacitor stores charge. The capacitor stores charge. Okay, it stores electrical charge. It can supply energy at a much greater rate. Okay, so it can supply energy at a more greater rate than the battery. Okay, at a more greater rate. Now, when flashlight unit is triggered, enough energy is allowed to the unit to emit a burst of bright light. So what happens when you take a selfie with the camera and probably in the dark, and the camera has a flashlight, you see a burst of light that comes from the flashlight. So it is powered, I'm talking about a photographer's camera now, it is powered by that capacitor and not necessarily the battery. Alright, so that can be like a good intro. Now, we want to look at how a capacitor is formed. Okay, now according to fundamentals of physics, okay, now according to the fundamentals of physics, now how a capacitor is formed. Now we want to look at how a capacitor is formed. Now, two conductors isolated electrically from each other. And from their surroundings forms a capacitor. Now, a conductor is a material that allows electricity to pass through it, or it conducts electricity, okay? So it allows electric flow to pass through it. Now, if you have two conductors that are isolated electrically from each other, okay, it forms can be used to form what is called a capacitor. Now, later in the study, we'll look at parallel plate capacitor. Okay, so just take note of this. So when capacitor is charged, the charges on the conductors of plates as they are called have the same charge. Now look at this. Now if you have a conductor, you have a conductor. Alright, so each of them are conductors. This one has a charge Q, this one will have a negative charge. Okay, so that's like trying to form a capacitor just for an explanation. Okay, so when a capacitor is charged, the charges on the conductor, so this is the conductor 1, this is the conductor 2. So the charges on the conductor or plate, so these conductors are also called plates. You can call it plate. So each of them will be just a plate. So when you hear plate in this kind of topic, it may be referring to conductors. Okay, so the charges on the conductors or plates, as they are called, have the same magnitude. Q. They have the same magnitude, but opposite signs. So take note of that. Alright, so we proceed now. We want to look at how much charge can be stored. Okay, now how much charge can be stored. Now look at in the capacitor. When you see a capacitor, how can we say that in this type of capacitor, this is the amount of charge that it can store? Okay, so because we have another capacitor that can store more charge. So how do we know the quantity of charge that a capacitor can store? Okay, so now for a capacitor, this is from college physics. Okay, now for a capacitor, the given charge. The given charge. Okay, excuse me. Alright. So for a capacitor with a given charge surface area, okay, the electric field at any point in the region, we're going to listen to explanations of this. Okay, in the region of the conductor is proportional to the magnitude. The magnitude Q of the charge on each conductor. Now what this is saying is that now if you have a capacitor, alright, so for a capacitor with a given charge surface area, now the electric field at any point in the region between the conductors. Now if you look at this, let's assume we have this as conductors. Now charge Q, charge minus Q. Now there's going to be electric field here. Okay, there's going to be electric field in between it. Okay, now it says the electric field at any point in the region between the conductors, okay, is proportional to the magnitude Q of, so this Q, let me just use magnitude Q, okay, so is it proportional to the magnitude Q of the charge on each conductor. Now take note, they must have equal magnitude but opposite direction. So if the the charge is doubled. If you have 2Q, you are likely to have more electric field. Okay? Remember, when the electric lines of force increases, the electric field you are saying increases. Okay? As the density increases, the electric field increases. Okay? Now, so let's come back to this. Now, so take note of this. When the electric field is proportional to the magnitude Q of the charge on each conductor. Now let's proceed. Now it follows that the potential difference between the conductors is also proportional to Q. Now, what this is saying, the potential difference is also proportional to Q. Now, that means if Q is increased, okay, if Q is increased, maybe it's doubled, it's multiplied by 1.5 for each part. Now, it also affects the potential difference. The potential difference between the conductors. Okay, so the potential difference is big. Okay, so it also affects the potential difference between the conductors. Now, we now want to look at, so this is also from correct physics. Okay, now we want to look at the relationship between C, Q, and V. For what is C, by the way? Now, so when we look at this, now remember, here I've said that how much charge can be stored. Okay, so that's the point we want to look at now. So we consider definition of capacitance. Now I didn't say capacitor, but capacitance. So what is capacitance? The definition of capacitance: the capacitor C of the capacitor is the ratio of the magnitude of the charge Q, okay, the charge Q on either conductor to the magnitude of the potential difference V between the conductors. Now, what are we trying to say here? Now, here you have the capacitance C of a capacitor. So a capacitor want to describe the capacitance of a capacitor. Okay, the capacitance C of a capacitor is the ratio of the magnitude of charge on either conductor. Remember, the conductor has equal magnitude, but obviously they are opposite sign. So the magnitude, that magnitude Q, okay, the ratio of that magnitude Q to the starting ratio, the ratio of magnitude Q to the magnitude of the potential difference between the conductors. So we say Q over V is C. So C is equal to Q over V. Now, here you can now say Q is equal to CV. Okay, Q is equal to 1 equal to 0.5, Q is equal to CV. So this formula takes note of this. Okay, and then write it down. So the capacitance of the capacitor is the ratio of electric charge Q to the potential difference between the ends of the between the conductors. Okay. All right. So what's the unit? The unit of capacitance of capacitor. The SI unit. So this is from collectivity. Okay. Now see on collectivity. Now the SI unit of the capacitor of the capacitance of the capacitor rather. The capacitance is called the SI unit of the capacitor is called 1 farad. 1 farad. 1 farad. Now, guys, you can write it this way, 1 farad. Now, 1 farad is equal to 1 coulomb per volt. 1 coulomb per volt. Look at this. This is in coulombs and this is in volts. So coulomb per volt. Okay? So coulomb per volt. That's SI unit. Now it could be written, so 1 farad is equal to 1 coulomb per volt. Now this farad could be written in other kind of using certain quantity. Okay, just take for instance, if one goes to buy a frozen food, you can say give me 1 kilo. Okay, 1 kilogram. Give me half a kilo, so 0.5 kilograms. Now, just like this kilo is deciding quantity. Okay, in terms of gram. Okay, so we can also use, okay, just like saying that 1 centimeter is equal to 100 centimeters is equal to 1 meter. Okay, so this is a kind of describing quantity. Now this 1 farad at times may be written as microfarad. This is microfarad. Okay, in that case, 1 microfarad is equal to 1 times 10 raised to power minus, okay, let me just write it like, is equal to 10 raised to power minus 6 farad. Okay, so in that case, we also have picofarad. So we have microfarad, we have picofarad. Picofarad is written like P farad. Okay, so in that case, you can write it as 1 picofarad is equal to 10 raised to power minus 12 farad. So take note of that. Okay, so it may be written in form of microfarad or picofarad. Now let's go to parallel plate capacitor. Parallel plate capacitor. So this is the type of capacitor, okay? Parallel plate capacitor. Now imagine you have a capacitor like that is formed by parallel plate. So this is imagine you have another plate under it. Okay, now you have 2 plates. Each of them having area A. Area of the plate is A. Area A. Okay. Now if the distance between them is D, the distance between them is D, and the potential difference between them is V. Potential difference between them. So taking, we have two plates, okay, and then each of them is having area A. The distance between the plates is D, and the potential difference between them is D. Now, each plate is having a charge Q. Now, let's assume for this first plate, under is here, okay? Let's assume we have charge Q. For this second plate, on top of it here, we have charge minus Q. Okay, so we have opposite charges, okay? Now, the symbol we use for capacitor, the symbol we use for capacitor. So this content is gotten from fundamentals of physics. Okay, so the symbol used for capacitor is just draw something like this, okay? So that's the symbol. Just draw it like this, okay? It will not cross this. So when you see a symbol like this, that's relation to capacitor. Now, so this is the parallel plate capacitor now, okay? Now the other point that I want you to take note of in that place is that the electric field magnitude in this region, or this region, for instance, excuse me, I want to this region, or this region, in between them, okay, in between that region, the electric field magnitude in the region between the plates is directly proportional to the electric charge per unit area of the plate. Now, so the electric field E is directly proportional to the electric charge Q per unit area. Is directly proportional to the electric charge Q per unit area, since the charge on each plate distributes itself evenly over the surface that faces the opposite plate. What that is saying is that the charge on each, like for the first plate, the charge on the second plate are evenly distributed across the plate, like under the plate. They are evenly distributed. Okay, so now it says electric field is directly proportional to the charge per unit area. So take note of that. Now, this quantity is known as surface charge density. Surface charge density. This is from college physics. Okay. So some of these contents, like what I explained here, is in college physics. Okay. So you may refer to this as now electric charge density, and it is denoted by sigma. Okay. So electric charge density is sigma. The sigma is equal to Q over A. It is the charge per unit area across the surface of the plate. Okay. Now, so for the one that's having a positive charge, it will be this. For the one that has a negative charge, it will be minus Q over A. Now, so we have E is related very simply to Q and sigma. So how do we write that? We say E is equal to sigma over epsilon naught, which is equal to Q over epsilon naught A. Now take note of this formula. Electric field is, now you know in this case this is derivation, so it was not equal to. Now if you now use equal to, there should be epsilon naught here. So in that case, E is equal to in fact, if you just know this, you can easily get this. Okay, if you know that this one is equal to this. Alright, so in other words, sigma is equal to charge per unit area. So if you now know that E, which is the electric field, is equal to sigma over epsilon naught. So from there you can write this. Okay, so just write the value of this. So which is going to be this. Okay. Alright, so let's proceed. Now epsilon naught, remember epsilon naught can be gotten from K over in Coulomb's law. K is 1/4 pi epsilon naught. 1/4 pi epsilon naught. Here epsilon naught is now equal to 8.85 and 10 power minus 12. Okay, so take note. Alright, so this is the value. So here of color physics. Okay. Now, so that's the value of epsilon naught. Alright, so if now let's just continue. If the distance between the plate is D. Now if the distance between the plate is D, V is equal to V is related to electric field by E times D. Okay? So in that case, D, which is potential difference, E is going to be 1 over epsilon naught Q over A times T. And that will be QD over epsilon naught A. Take note of that. Now, how do you get that? You know that this D is still this D, okay? No more things. But E is this, okay? So, and then you get that. Alright, so when you have, it depends on the parameters you are given, so if you know these formulas by heart, okay? The parameters you are given, and then you use the formula. Okay? At this level, there may be no more technical, deeply technical questions that relate to this. Alright, so just take note of those formulas. Alright, so we proceed, and then we have another aspect now. So let's now go to capacitance of the parallel plate capacitor. The parallel plate capacitor. Now you see how a parallel plate capacitor looks like. Okay, by step. So the capacitance of a parallel plate capacitor in vacuum is directly proportional to the area A of each plate. And inversely, this content is gotten from college physics. And inversely, proportional to their separation. Separation D. Now, what that is saying is that we have C equals to Q over B. This is equal to epsilon naught times A over B. Now, take note. Now, the capacitance of a parallel plate capacitor, this formula you are likely to use it, okay, when you are solving certain questions in to find the capacitance of the capacitor, to find the area of the plate, to find the distance between the plate. To take note of the formula, the capacitance of a parallel plate capacitor inversely is directly proportional. Now, take note of this relationship. It's directly proportional to the area. It's directly proportional to the area of each plate and inversely proportional to the distance. So, in other words, if the area of the plate increases, since it's directly proportional to the area, if the area of the plate increases, then that means the capacitance will also increase. If the distance of the plate increase, okay, if the distance, that means the gap between the plates, if it increase, that means the capacitance will be reduced because it's inversely proportional to the distance. Now look at the relationship. C is equal to Q over B. Okay, that has been described before. And then you know that D is this, which is 1 over this, Q over A, this. Now, if you now bring this value, you bring it here. Okay, so let's see what we have. So we are going to have, so I will write this first. So we have Q divided by QD over epsilon naught A. So then that means you have Q times epsilon naught A all over QD. So Q cancel Q, so we are going to have this. Okay, epsilon naught A over D. So take note of that. So that formula is really important if you are going to solve questions, especially if the question is related to using this formula. Okay. Now, so we take an example now. Let's take an example. A parallel plate. Example gotten from college physics. A parallel plate capacitor. A parallel plate capacitor has a capacitance of 1 farad. Okay, and the plate are 1.0 millimeter apart. So this is written as 1.0 farad. Okay. And the plates are 1.0 millimeter apart. Okay, what is the area of the plate? Now you know that C is equal to epsilon naught A over D. Now they want us to find the area of the plate, and then they have given us C. Take note, C must be in farad. C must be in farad. A must be in meter square. A must be in meter square. D must be in meter. So now let's solve. Now we use C as subject of the formula, so we have CD C times V over epsilon naught. Now we apply C is farad, so we have 1.0 times D is in millimeter, so we convert it to meter. That will be 1 times 10 to the power minus 3 all over 8.85 times 10 to the power minus 12. So if you know that value by heart, so when you solve, you're going to get 1.1 times 10 to the power 8 meter squared. Alright, so endeavor to solve more questions that relate to this. Okay, thanks for watching. Bye for now.